All right, guys, this is the last video before this next test. This is video 4 on slope fields. I personally find it to be one of the most kind of fun and different ways at looking at differential equations, and I hope you do too. So first of all, we want to look at how literally it's a field of a bunch of slopes that are graphed. So let's take a look at those. So it is an easy way to kind of figure out what a solution looks like to a differential equation. Remember, a solution to a differential equation is when you have a dy dx and you go back to just a y equals scenario. This is considered the solution. So basically, we're using the slope fields to kind of see what we think the original equation had looked like, right? Okay. So um, in this first guy, we have our slope field, which says that my slope is always equal to just the y value. Okay, so that should mean that no matter what I plug in for x could be anything, the y value is what we're going to get out for our slope. So no matter what, like for example, if I went over to the point x equals 2, y equals 0, so that point right there. There is no place to plug in an x, so the x does not play a part in determining the slope, but the y does. So at that point, my slope, if I plugged it in, would be 0, which is a horizontal line. So in fact, anywhere you have y equals 0, you would have a horizontal line. If I go to like, let's say, maybe 1, 1, and I look at that point, well, again, the x doesn't affect it, but the y does, so my slope there should be 1. So notice you have this kind of up 1 over 1 slope. And then the taller you get, the more steeper you get, and so on and so forth. And you can do the same thing, but into the negatives. Okay, let's take a look at this one. For this slope field, now this is a little different because the slope is determined by both x and y. So you'll notice a lot of times we're going to start looking at where our slope is horizontal because that's the easiest way, which is when our slope is 0. So first of all, I want to draw your attention to the fact that the slope is 0 along this kind of line here, okay? Now imagine this. Imagine that we set this equation for slope equal to 0, and we solved. What do we get? We get that it's 0 basically along y equals x. Guess what this is? This is the line y equals x. So you would expect your slope to be 0 there, so you can kind of tell that it's going to match up. But again, if I wanted to test some points, I could plug in like the point, let's see, what if I went -1, -2? So there's that guy, -1 for the x and -2 for the y. If I plug those in, I'd get -1 minus the y value is -2, so that would be -1 plus 2 or 1. So notice my slope through there is 1. In fact, it's 1 this whole time because of the relationship between the values being slightly off. So, okay, we're going to spend time being able to recognize what slopes go with what slope fields go with what, and how to draw them. So in the first one, well, we could ask ourselves, when are we going to have vertical? In fact, I'm going to add a problem to this. I'm going to ask first, when do we have vertical segments? And we could also look at for when we have horizontal segments. I'm going to do both. Okay, so we'd have vertical segments when our slope has a denominator that's 0. So vertical slope segments would be when the denominator is 0. So I could literally take the denominator, set it equal to 0. Because I have two variables, I'm only going to be able to get a relationship, but that's fine. So when I solve for y, I could have solved for x, but y is what we're more comfortable with. I get -2x. What does that mean? That means you would expect along the line y equals -2x, which y equals -2x kind of looks roughly like this, guys. You would expect your slope to be vertical, which basically means there wouldn't be any lines because we really don't have vertical slopes, but that's how it would be. So your slope field would look perfectly vertical on that line. Other places it's going to look different. Okay, what about horizontal segments? Well, if you want your horizontal segment for your slope, then as you guys know, that would mean I want the slope to be 0. So the top would be 0. Now this one's a little trickier to solve because I have things that are affecting both of these values. So like I could factor out a y and get x squared plus y. I could set that equal to 0, and so I could get y could be 0, or I could get this idea of x squared plus y being 0, so y would be -x squared. So what would that mean? That would mean I would expect to see horizontal segments at y equals 0. Y equals 0 is here. So kind of along this x-axis, this is when y equals 0. I would expect to have a horizontal slope there. And then I would expect to see a horizontal slope anywhere that looks like negative x squared, which you guys know that negative x squared looks like this downward facing parabola. So you would expect to see a bunch of horizontal line for slope. In fact, I'm going to get rid of the parabola. You would expect to see a bunch of horizontal slopes that are in kind of the shape of a parabola, right? And they're all horizontal. And then other stuff happening around that. But these zeros and these vertical slopes are really helpful when you're trying to like match up a slope field. Okay. What if I just wanted slope at a particular point? Well, if this is my slope relationship and I want to know what the slope field would look like at negative 1, 3, I literally just plug in the points negative 1 and 3. So on this guy, I end up with negative 1 over 1, negative 3, excuse me, over 1, so negative 3. So I would draw at negative 1, 3 a slope that looked somewhat like negative 3. So it's steeper than negative 1. Negative 1 would be perfectly at a 45-degree angle. So negative 3 might look something like this. Just to show you in contrast, let's do like, what if I did negative 1 but 2? Well, if I did negative 1, 2, I end up with 2 on top, a negative, and then I end up with a negative 1 squared, so I end up with a negative 2 slope. So if I was going to graph that, negative 2 is a little less steep, so maybe something like this. And then it kind of starts to get a little flatter and so on and so forth. And so you'll notice these when we start to look at the slope fields all together. Okay, so in this one, I've got, now this one we're going to do a little bit more with it. So here's my relationship. Whoa, I've got some cosines. That's fine. I've got some, y values. So if I wanted, it says on the axes provided, sketch a slope field for each of the 9 points. See them all? Okay. So the first thing I'm going to do is plug in, I'm going to try all these values up here where if you'll notice all of these have a y value of 1. Why is that so nice? What's going to happen when you plug in 1? You're going to get 0 squared times cos. Well, who cares what this is? If this part comes out to 0, the whole slope is 0. So basically, anywhere this y value is 1, I know I have a horizontal slope. Okay. Now let's move on. We'll go down here to the y-axis. If I plug in, let's start with our origin. So 0, 0. If I plug in 0, 0, I get 0 minus 1 squared cos of pi times 0, which is just cos of 0. That's a 1. That's a 1. So I get 1 times 1, which is 1. So my slope at 0, 0 should be 1, which is that positive horizontal line. Let's try 1, 0. If I plugged in 1 for x and 0 for y, I get 0 squared, or sorry, 0 minus 1 squared. I get cos of 1 pi, because I remember I'm plugging in the 0.10, and I get 1 times cos of pi is negative 1, so my slope here would be a negative 1. And I can repeat that process throughout. And what you end up with is a bunch of different slopes. And so you can kind of see them and you can test them to see if you could have gotten some of them right. Okay. It says there's a horizontal line with equation y equals c that satisfies the differential equation. So to satisfy it, you're looking for a solution. Well, if we know it's horizontal, then we know that that would mean that the slope would have to have been 0. So if I want to look for my slope to be 0, up here, what y value would make a horizontal line? Well, you can solve, I suppose, if you want to, when that would come out to 0, and that ends up being at y equals 1. So if y is 1, I'm always going to come out with a horizontal line. Okay, find the particular solution to the differential equation. Now this you guys already know how to do. If I want a particular solution, then I need to do the antiderivative. So we've got a little bit more work to do on this one. So I need that equation. I've got y minus, okay. So I've got dy over dx equals y minus 1 squared cos pi x. This is a little involved. So let's see what this looks like. We're going to separate the variables. 1 over y minus 1 squared dy, and then cos pi x dx. So integrate both sides. This guy's a little messy. I would probably rewrite this as y minus 1 to the negative 2 before I integrate it. This side is pretty easy. I do have to do a u substitution here, so be careful but du is pi dx, so it's not terrible. So I'm going to get a 1 over pi du dx equals dx. So I'm going to have a 1 over pi out front, and then the integral of this is going to be sine of pi x. And of course, plus c. Now let me integrate this side. So I have to go up by a power and divide. So I end up with, and the u here would be a straight relationship. So I technically have a u substitution here, but it comes out just straight dy. So I've got, let's see, we said go up by a power, y minus 1 to the negative 1 and divide by the power, so I get a negative. So I get this guy so far. So then if I want the particular solution, I'm going to plug in my point. So when y is 0, I get negative 1 to the negative 1. There's a lot of negative ones. Remember, this just means I get negative of 1 over negative 1. So this all ends up to be a positive 1. And then here, if I plug in 0, I get 1 over pi times sine of, that'll be a 0. Sine of 0 is 0. So we end up with c equals 1. So I have, let's see, right here, I have negative, I'm going to change that to 1 over y minus 1 to the first power. So I'm going to rewrite that a little nicer, equals 1 over pi sine pi x plus 1. So I just plugged everybody back in. Okay. So in a minute, I can flip this upside down, but I'm only allowed to flip this upside down, like put the y minus 1 on top, if this is all written as one term, and it's not. Because right now, I technically have this with a 1 over pi, and this is a 1. So if I want to put them together, I need common denominators. So I'm going to leave this guy as sine pi x, but technically it's over a pi. And then to be able to add 1, I would have to change this into a pi over pi by multiplying. So it actually ends up being plus pi. So I hope you guys see that. I took the 1 and I made it have a common denominator of pi. That way I could put them together, because then I can flip this side and I can flip this side and it would still be true. You can only do that if the entire side is one fraction compared to one fraction. And then of course this still had a negative. And so then I'll bring the negative over and make it negative pi over this. And then I have y minus 1. And so then I'll add 1. So there's my final particular solution. Okay, in our last couple of examples, we're going to look at the actual entire slope fields. So in this first one, I ask you which of the following could be the slope field for dy dx equals cos. So the major mistake people make is they think that this is what the graph should look like. Remember, this is not the graph. This is how we get the slopes. And the original graph is what I get if I would take the antiderivative of this. And because there's no y involved, the antiderivative of cos is just sine. So you're really looking for the graph that looks like sine. So this graph kind of looks like this. This graph kind of looks like that. This one kind of builds, if you can see that. And then this one is kind of wonky. Okay, the only one that looks like sine, which sine is supposed to be at equilibrium at 0, is this guy. See that? Whereas this kind of looks like it's a negative cosine graph, and then these aren't even it at all. So just be careful that you don't think that that's the graph. Okay, and on this last one, we want to see which one of these could be the differential equation that gave me this slope field. All right, well, I like to use any horizontal lines that I see. So see how this here, the slope is 0? Well, the slope is 0 when it looks like it's y equals 2, guys, but it's not. Careful. Notice that this is 3, which means this is 2, and that's a negative 1. That was a big mistake I made the first time I saw this problem. So this is 0 when y equals negative 1. This whole time y equals negative 1. And so if we go over here and we look for things that would make this come out to a slope of 0 if y was negative 1, let's see, this would not have affected it because there is no y. This one would definitely be 0 if y was negative 1. And if y was negative 1 here, not necessarily a 0, so no. This one, yes, because if you think about it, if you factor out an x, you get that, which again, of course, would be 0 every time you plug in a negative 1. So now the question is, which of the two? This is where you're going to notice you also have a slope of 0 at every place that x is 0. So that is why it would also be true for A. All right, good luck on the problem sets.